Hello, I'm Bernie. I'm from NewT.EXE FTC 21780, and I'm the team captain hardware lead.
I'm Solomon. Solly. I'm from the same team, software lead, I guess.
All right. So at the beginning of the season, there were a couple of goals that we wanted our robot to have. First, we wanted it to be able to be small and as small as possible and maneuverable, so we can move around all the junctions. Second, we wanted to minimize drivetrain movement, as we saw that in previous games. Drivetrain movement was generally the slowest part of the game. And finally, we want a low center of gravity. Since we'd be sending a lift really high, we wanted to not tip. So starting off with a robot, we have our drivetrain, which is a 14-inch by 16-inch Mecanum drivetrain, so a bit smaller than the size limit, which lets us easier get around the field. Using Mecanum wheels, which allows it to move in any direction, meaning that we don't have to turn before moving sideways. And finally, it has a set of 3 Adanju pods, allowing us to accurately localize ourselves during the game. For intake, we went for an extendo intake. Our intake is not a parasite that can extend 4 feet, and this lets us minimize direction movement and occasionally even, for example, on the close high junction, even cycle in place. Went for claw because what that lets us do is it lets us sort of like run into the cone and grab it instead of having to position ourselves directly over it, saving time on alignment. And the cool thing about our claw actually is that it can over center, meaning that once it's closed, it's really hard for something to pull it open unless the robot wants it to. And finally, our intake arm is counter sprung, meaning that we have elastic tubing in this case, pulling it back towards the vertical position, and this helps offset load on the servo. After our intake grabs it, it transfers it over to our outtake, which is a passive outtaking mechanism mounted on a set of hybrid double reverse 4-bars. Now, these double reverse 4-bars have a virtual 4-bar section on the top and a full 4-bar section on the bottom. And since the virtual 4-bar section uses plastic chain and only one linkage, it's light, allowing us to save on weight, while the full 4-bar on the bottom is heavier and sturdier. And what that lets us do is it lets us have a good balance of stability and weight, as well as lower. Since we put the heavier section on the bottom, it allows lower center of gravity. And for our actual outtaking mechanism, we went for a passive outtake where the cone or the junction itself takes the cone off the pole. And that way we were able to put depositing and retraction into one motion, saving time, and lets us use the cone itself to align with the junction.
So, in autonomous, one of our biggest challenges was cycling 5+1 cones onto the align side junction, because we have to simultaneously move a drive in a spline, move the intake, and move the outtake. And to coordinate this, we use Roadrunner with multiple trajectory sequences and a custom program FTC's command system, which I'll explain later. And some of our modes have the ability to abort when we detect that a cone is missing or we're running out of time, to make sure we have time to park and avoid penalties. So our output inheritance structure allows us to avoid duplicate code, which means that if we change code in one place, it'll change everything we need rather than having to remember to change a bunch of separate places and keep them in sync. So in our code, we have new auto implementing the overall structure. Then we have a separate auto for each position for the junction, which define the trajectories. We have different intake-outtake sequences, depending on how many cones you want to try to deposit if something goes wrong. And we have left and right, which just for the 2 sides. And so FTC's command system, so we made various changes. So first of all, the command system, lets us coordinate commands like more advanced state machine, and we split up some features, merged other features. One key thing we did was change the callback system to better improve its support for logging, so it can output information about what's going on to a log file, so you can look at it later and figure what the robot's doing and to help with debugging. In our intake, so we have a sensor on the end, that a distance sensor that detects how far the cone is, And teleop, it automatically slows down as it gets close, and then auto, when it gets close, it detects how far it is and calculates the target position accordingly. And in both modes, when it gets very close, it stops and closes automatically. Vision, we use April tags because they're easy to detect, and we found an open source implementation. We use 3 of them so it can detect from all angles, and we use the closest match to avoid detecting your opponent's cone. Any questions?
Sure. So our robot this year, this is actually the first robot we made that's completely made out of metal. And for this, we actually built our own CNC machine. And over the past 3 seasons, we've been slowly testing on various materials. And this year, we're finally able to get a good profile for aluminum. And what this let us do is since we can machine the aluminum parts in-house, it let us iterate extremely quickly on our subsystems. For example, our lift didn't originally have this section in the middle. This section in the middle was actually added to add clearance for this servo on the top. But because we were able to machine aluminum in-house, we decided that we would add this section, even though it was fairly close to competition. And that helped improve the reliability of a robot.
We had a couple questions come in from chat, by the way. First one from Screen 404. What was the difficult part of using extending intake?
On the hardware side, it's definitely wiring. Because we also went with a double reverse 4-bar, that means that the side sections of a robot are basically all taken up. And we couldn't easily run a wire loom or a huge scissor lift wiring thing in the middle, because that's also where the arm went back. So we went through a ton of iterations of this wiring, and what we eventually ended up with is we attached it all to the underside of our slide inserts with a bit of elastic tubing in order to make sure that when it retracts, it sort of falls into the right place for it to not get tangled up.
I guess on the software side, the biggest thing is that the farther we extend the intake, the more precise we have to be about our robot's rotation in order to line up with the cone properly.
I'm going to combine these 2 questions into one here from Seedling Sinton, asking what was the most difficult challenge you faced this past season? And then Civ adds on, is there anything you would have done differently had you had the chance?
Sure. I'd say probably our most difficult challenge on the entire team was probably getting the 1+5 alliance tie to work, which was a challenge both on hardware and software. Mainly because as the season went on, our Masumi slide slowly started getting more and more loose, and it started drooping, which meant that we needed to make some additions to our robot. So we added this set of idler wheels at the front in order to prevent drooping. And also, if I were to do something differently, I'd probably include some sort of turret mechanism in the outtake. Right now, it only deposits out the back, and that means that we have to constantly turn when trying to cycle on the alliance high junction. We actually did make CAD for a turret mechanism, but we didn't end up getting enough time to implement it.
In the software side, I guess one thing that would have been good to implement earlier is using the same control flow structure throughout, because our code is currently uses different ones in different places, and it's hard to get we have multiple software team members, so it's hard to get everyone to agree to change, especially once we have working code. We don't want to change it unnecessarily and potentially break anything. So if we agree decide on the start, that could help.
All right, chat, we'll give it just another minute if you got any more questions come in. Otherwise, NewT.EXE, anything else you'd like to wrap up with on your presentation?
I guess in terms of difficulties, I guess one thing I want to mention is that transferring took us a while to debug, as it always does.
Yeah, transferring was a mess. It worked perfectly well in CAD, but in the real world, there are some issues. For example, one big issue was there was some backlash in our claw mechanism, and what would happen is, so what a robot does is it lifts the arm and brings the slide back and pivots the claw all at the same time, and that means that the cone has to move very fast, and this backlash would mean that it wouldn't move precisely where we wanted it to go, and it would sometimes miss the transfer. We eventually we eventually iterated on these claws on our outtake, and what we were able to have them do is have them automatically funnel incorrect transfers into the correct position, or inaccurate transfers into the correct position to deposit, which helped solve the issue.
All right, well, Newt, thank you so much for appearing on there and chat. Thanks for your questions as well, too. We're going to be heading over and getting ready in just about 6-7 minutes for our next team, which is 8393, the Giant Dice Phallic Brainstem Robotics team. Thanks a lot, Newt.
Thank you.
Thank you.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. At Kettering University, over 30% of the student population was in high school robotics. These same students have received a portion of over $7 million in FIRST scholarship. Scholarship applications will open in September. Get ready to go pro and get more information at kettering.edu/first. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.